Hello everyone. In this lecture I shall discuss the Cauchy integral formula generalization or extension. So in this previous lecture what we have studied? We have studied if fz is analytic within as well as on a simple closed path, right? Then for any random point z0, right, means suppose you are given a simply connected domain C you are given, right, and the function fz is analytic throughout. The function fz is analytic everywhere, inside as well as on the boundary also. It is analytic everywhere as well as on the boundary. Let z0 be a random point within C. Let this z0 here be a random point. Okay, z0, we take a random point z0 here. Let z0 be any random point here, right? Suppose my z0 is a random point here. This point is suppose my z0. Okay, this is a random point here. Then in previous article we have studied. Now it is simply what is fz. What is fz we have studied. So what is fz? We have studied this Cauchy integral formula we have simply studied. This integral is fz is equal to here 1 by 2 pi I integral c fz by z minus z0 dz. Now here we have to learn, right, here we have to learn if it is derivative here, derivative of f, and if it is the power here 2, means power is here 1 plus 1, power is 2. Then we have 1 by, means here factorial 1 here. Factorial 1 by, I can say it is my factorial 1, okay. 1 factorial divided by, or I can write like this, it is here factorial 1 by 2 pi I into this. If power 2 is here 1 plus 1, so this power here is here 1 plus 1 power, right? This power is here 1 plus 1 means 2 when the power is 2. Now when the power is 3, right, when this power is 3 it is 2 plus 1, then it is factorial 2. The second derivative here is factorial 2 by 2 pi I integral c fz by z minus z0 to the power 3. So likewise, if the power is n plus 1 here, then factorial n is multiplied, right? So now in view of this, what is our intention? Our intention is to evaluate here integral c fz by z minus z0 to the power n plus 1, this power function here in the denominator. Then here we have this is equal to here 2 pi I, bringing this to left hand side, it is 2 pi I by factorial n f nth derivative at z0. So our intention is to learn this, right? If we have a function like this fz by z minus f0 is something, fz is something different function, it is analytic, and randomly z0 is any point in this path, within this path, and the denominator it is z minus z0 and the power is n plus 1, then it is 2 pi I by factorial n f nth derivative at z0. So this is the idea, okay. So this will help you to find the derivative of the analytic functions, right, nth derivative of the analytic functions. So before the details of the discussion, let me to introduce myself. Professor S.K. Paikray, Susanta Kumar Paikray, currently working as a professor of mathematics at Veer Surendra University of Technology, Visut, Burla, Sambalpur, Odisha, India. So without much delay, let me to discuss some examples so that your idea will clear. Now suppose you are asked to solve a problem like this. Now this integral, if I write, first you understand the path here. The path here is a circle with center at 0 and radius 2. Now you think about the denominator here. The denominator is I, z minus I whole square. Means if I equate it to 0, then I find here I is a point here, I. So this I is here, right? Now what about my fz? If I write it, this integral I is equal to, right, integral I is equal to integral c fz by z minus z0 to the power 1 plus 1. This power is 1 plus 1. So this is my fz now. This is my fz now, right? So this fz is simply a polynomial. Here fz is equal to here fz is equal to zq minus 2z plus 1 is analytic everywhere, right? Is analytic everywhere in C. So this is my C here. So it is throughout, it is analytic everywhere in C, right? And my z0 is equal to I. This is a random point here. Is a point lies inside, is a random point within C. So within C. So thus we are ready to apply the Cauchy integral formula extension. Thus by Cauchy integral formula extension, what we are getting, this I is equal to here 2 pi I by factorial n, 2 pi I by factorial n, nth derivative of, means n is 1 here, and what is here n? N is 1 here, so nth derivative of, right, fz is here zq minus 2z plus 1, right, at the point, it is at the point here z0, at the point here z0. So z0 is here I here. So this is equal to 2 pi I, n is here 1 by factorial 1, it is d by dz of, it is nth derivative of, right, it is d by dz of zq minus 2z plus 1 at the point z is equal to I. So this is equal to 2 pi I. If you differentiate it, it is 3z square minus 2, right, at z is equal to I. So it is 2 pi I into 3 into I square minus 3 and minus 2. So this is minus 10 pi I. So coming to the solution of example 2, first we have to understand this given path. The given path is a closed path, circle with center at 0 and radius here 1 here. So now here pi by 6 is 3.141 by 6, it is around 0.52, right, it is around 0.52. So 0.52 is here, is not it? 0.52 is here. So this lies over here, right? This is point, simply a point. So no harm, I can take this is my fz. I can take this is my fz here, okay? So I write, let this integral be I. So let my I is equal to integral c fz by z minus z0 to the power 3, right? Where fz is equal to sine square z, which is analytic everywhere in C. It is analytic everywhere, means it is analytic everywhere in C we need, right, in this path, within this path here. The path orientation here is given clockwise orientation. So the integral will be negative of the integral, okay? So now what is your z0? Z0 is equal to here pi by 6, and what is your n? N is equal to 2, because this is n plus 1, right? So by Cauchy integral formula, thus by Cauchy integral formula extension, here integral I will be equal to 2 pi I by factorial n, nth derivative of dn by dzn f z at the point z0. At the point z0. So I can write it 2 pi I by factorial n is 2 here. N is 2. It is d square by dz square sine square z at the point at z is equal to here pi by 6. So this is equal to here pi I. Now this we write it minus because the orientation is clockwise orientation, so I write minus. So if I once differentiate it, sine square z is 2 sine z, again sine z is cos z, 2 sine z cos z is sine 2z, okay, at pi by 6. So it is minus pi I, derivative of 2 sine z is here 2 cos 2z, right, at pi by 6. Z is equal to pi by 6. So this is equal to minus 2 pi I into cos pi by 3. So cos pi by 3 is here half, is minus 2 pi I into half. So this is minus pi I, right, because this integral is in clockwise, so we have a minus sign, right. So let us evaluate few more examples. Now coming to the solution of example 3, first we have to understand this path here. So path is a circle, center at I and radius 2, right. So we take this path. Center, this is my origin 0, so it is at I. At I, radius is 2, so it will come here up to minus I. This is one distance, this is one distance, so it will come up to here minus I here, and it is here it will come up to 3I. It is 2I, it is 3I. So this is a path is like this, okay. This path is like this. This is my minus I. This is my minus I easy. So this point is my minus I. So now you see. So this integral I, if let I mark it I. So I is integral C dz by z minus 2I into z plus 2I. This is the whole square again. Now here 2I, this will come up to here 3I. So 2I is a point here. So 2I is here inside. But what happens to here minus 2I? Minus 2I is my here. So it is outside. Right? It is outside. So this minus 2I will not affect the analyticity of the entire function. So I can take this as my fz. So this minus 2I will not affect. So I can take this, right? I can take this as my fz, right? This as my fz. So this is your fz. So this is equal to, you can write it, integral c 1 by z plus 2I whole square divided by z minus 2I whole square to the power 1 plus 1 or whole square. So this is of the form integral c fz by z minus z0 to the power n plus 1, right, with here fz is equal to 1 by z plus 2I whole square, and it is not analytic as minus 2I which is outside, which is analytic everywhere in C, right. The orientation is positive orientation given, means anti-clockwise. So therefore by Cauchy integral formula extension, here I will be equal to 2 pi I by factorial n, right, by factorial n. F nth derivative means first derivative at the point 2I. So this is what we have to find, okay. So what is the first derivative of this? So this is equal to 2 pi I into d by dz of here 1 by z plus 2I whole square at the point 2I. So this is equal to 2 pi I, and the derivative of this is here this to the power minus 2 into 2 by z plus 2i whole to the power 3n plus 1 means 3 here. Okay, at the point 2i. If I substitute z is equal to 2i, it will be your minus 4 pi i divided by 4i whole cube, right? So this is equal to pi by 16 here, right? So this is your answer, pi by 16. Now let us discuss the Cauchy inequality and ML inequality. Now coming to the Cauchy inequality, let fz be analytic inside and on a circle C of radius r and center at z0. Then fn z0 is less than equal to n factorial m divided by r to the power n. So here we have a circle center at z0 and radius r. Okay, radius r, and fz is analytic everywhere inside and on this. Okay, and if m is the upper bound of your fz, then we have to prove it. Now if you want to prove it by Cauchy integral formula extension, what we are getting here, fz0, f nth derivative at z0 is equal to n factorial by 2 pi I integral c fz by z minus z0 to the power n plus 1 dz. Now if I take the modulus on both sides, so that means here fn z0 mode is equal to n factorial 2 pi I factorial modulus of this into integral here modulus of this, right, fz by z minus z0 this mode dz mode. One more step let us perform. Let you omit this. We take the modulus of the entire thing. Okay, we take this modulus of the entire things. You know integral fz mode is less than integral fz mode. Why it is so? You know z1 plus z2 mode is less than z1 mode plus z2 mode. Triangle inequality. So summation of zn mode is smaller than zn mode summation. So integral is also, it is the summation process, right? Is not it? So this, while I take this modulus inside, so it will be smaller than equal to, right, n factorial by 2 pi I mode, and if I take the integral to inside, fz by, this is n plus 1, this is your n plus 1, fz by z minus z0 to the power n plus 1 and dz mode. Okay, so that is equal to, I can write, it is your factorial n, and I mode is 1, it is 2 pi, and it is integral c, it is fz mode, and it is your z minus z0 to the power n plus 1 mode, right, modulus of this, and this is your dz mode, right. So now what is your dz mode? Here path here is c is z mode equal to r, c is your z mode equal to your z minus a mode is equal to r, z minus a mode is equal to your r, right. So the denominator is r to the power n plus 1. So what is z? Z is r e to the power I theta. If we put this is the parametric representation. So what is dz? Dz is ri e to the power I theta d theta, right. So what is dz mode? Dz mode is ri e to the power I theta d theta mode, right. So this mode. So I mode is here 1. So this is equal to r. I mode is here 1. E to the power I theta mode is cos square theta plus sin square theta root over, it is 1. So this is simply r d theta, right? So what you can write, it is n factorial by 2 pi, it is integral c, right? It is fz mode divided by, this is here z minus z0 is here r, z minus z0, right? Z minus z0 is here r to the power n plus 1, and dz mode is nothing but here r d theta, and the limit of integration, since this is a circle, 0 less than theta less than 2 pi, so this is 0 to 2 pi. Now your fz mode is less than equal to your m, right? So which is again less than equal to your n factorial, this is m by 2 pi, it is 0 to 2 pi, right? Here 1 by r to the power n, this r and 1 cancelled here, it is d theta. So r to the power n can be taken out because we are integrating with respect to theta. So n factorial m by 2 pi r to the power n, it is your integration of d theta is theta 0 to 2 pi. So this is equal to n factorial m 2 pi r to the power n, and it is 2 pi minus 0, right? So 2 pi cancelled. So this is n factorial m by r to the power n. So what we are getting? We are getting integral here fn z0, right? Here fn z0 mode is less than is equal to n factorial m by r to the power n. So this is the ML inequality, where m is the upper bound of the integrand. Okay, now let us discuss one more inequality. This is the ML inequality. Now coming to the ML inequality, let fz be an analytic function on a contour C, but here it is not necessary the path is closed. But earlier what we have seen? Earlier we have seen the path is closed, inside add-on closed path here we have seen, but here the path is not necessarily closed. So we can not necessarily close, not necessarily closed path, right? So and let the length of this path be L, then and m be the upper bound of the integrand fz, then the modulus of this integral is less than m into L. Suppose you are asked to evaluate integral c real z dz. C is the shortest path from 0 to 1 plus I. So first you draw the path. So this is 1 point, 1 plus I means here 1 point here. So we have a path here. Right? So from 0 0 to this. Actually this is not the line for y is equal to x. Right? So if you put this is your line C, path C. Put your x is equal to t, implies y is equal to t. So zt is x plus iy. So x is here t plus it, and x coordinate here we are taking the first component. So it is 0 to 1, 0 less than t less than 1. So this is what is your real part of. Now what is your dz you find. What is your dz? The derivative of t is 1, derivative of it is I, and dz by dt is this. So I dz is this dt. Now what is your real part of z? So real part of z here is my t here, right? So this integral I becomes here. So therefore your integral I, this integral I is equal to integral 0 to 1, real part of z is here t, into dz is 1 plus I dt. So this is equal to 1 plus I t square by 2, 0 to 1, it is 1 plus I by 2, right? 1 plus I by 2. So now what is your integral fz mode? So integral, this ML inequality is integral c fz, integral c, right? Integral c fz dz mode. So if I evaluate this in modulus of this, so this will be 1 square plus 1 square by 4 root over. Okay, so this is equal to root 2 by 2, 1 by 2 root 2, right? So this is direct, your direct integration, direct evaluation. Now to verify your ML inequality, Now to verify your ML inequality. Verify the ML inequality, we have the length of the path, length of C. So this is the distance from 0 to 1 plus I, right? It is your L is equal to 1 square plus 1 square root over is your root 2. Now what is your real part of Z? The real part of Z is your X. So this is your X. So real part of Z your X. So your real part of Z, Fz, is your real part of Z. Okay. So it is your modulus of X. Is it not less than 1? So I am getting M is your 1. So what I am getting? So integral C Fz dz mod. Right. What is the actual integration? It is by 1 by 2 root 2. But is it not less than your M into L? What is your M? M into L. What is your M? M is your 1. L is your root 2. So is it 1 by 2 root 2? Is it not less than your root 2? Right. So this is what the ML inequality. So ML inequality just gives, right, without integration, it just give you a upper limit of this integral, right? So what is the role of ML inequality? So ML inequality here is, right, without being integration, we just find an upper bound. So now after integration we find the answer, but here without integrating we just find a upper bound. So this is the role of your ML inequality. So once Fz is analytic on a contour, the contour may be closed or open, that doesn't matter. Then without evaluation of the integral, we can estimate an upper bound of the integral. So this is what the meaning of your ML inequality. Okay. So let us close this lecture here. So in the subsequent lecture, I discuss the residue, calculus of residue. Okay. Calculus of residue. That means in the upcoming lecture I should discuss the evaluation of integral, residue integral. I will discuss residue integral. So this is another direction to find the integration. So the same integral can also be performed by the residue integral, but it will help you further to evaluate the contour integration, right? It will help you to evaluate the contour integration, right? So this residue integral is based on the Cauchy residue theorem, which will further help us to evaluate the contour integration. Contour integral is used to evaluate the real integral. Maybe the integral is improper, right, of this type. Suppose you are asked integral minus infinity to infinity sin x by x. This is a improper integral. 0 to 2 pi cos theta by 2 plus sin theta d theta. So this type of real integral, which are complicated by earlier means, we use the residue integral, okay, and which will lead you towards the contour integration to evaluate the real complicated integral, basically the improper integral. So this is again the important aspect of the complex analysis, right? So this residue integral can also be used to evaluate this integral, what we did by means of the Cauchy integral formula and Cauchy integral theorem, etc. Right? Again, this residue integral has another perspectives to evaluate the real integral, right? So let us close this lecture here. So at this stage, my appeal to all of you is that if you feel this lecture is useful and interesting, please like and subscribe to this channel, which will boost my motivation to upload subsequent lecture for your benefits. Thank you all.